Welcome back to the Deep Dive, where we plunge into a stack of sources to extract the most compelling insights tailor-made for your curiosity. Today, we're not just exploring a topic, we're embarking on, well, the most profound journey imaginable, the story of you. Just take a moment and consider the sheer, almost impossible unlikeliness of your existence. Right now, you are a sentient human being on this particular blue planet at this specific moment in cosmic time, listening to these words. It's a chain of events so delicate, so improbable that it almost defies belief.
It's an astonishing thought, isn't it? Our sources really underscore that for the past 3.8 billion years, that's 3,800 million years, every single one of your ancestors on both sides of your family tree had to survive. They had to find a mate, they had to be healthy enough to reproduce, and crucially live long enough to pass on their genetic material. Not one could be squashed, devoured, drowned, starved, or even wounded in a way that prevented that tiny vital spark from reaching the right partner at precisely the right moment.
It's incredible how delicate that balance was. The source material highlights this, saying the tiniest deviation at any point could have altered everything. We could be talking about you licking algae from a cave wall or, my personal favorite, lolling walrus-like on some stony shore. So beyond just biological luck, what does this cosmic tightrope walk teach us about the nature of our reality, about what it means to be here?
Well, it fundamentally reframes our perception of normal, doesn't it? What we consider stable, a given, is actually the outcome of an astonishing number of precise physical and biological parameters aligning over billions of years. The insight here isn't just luck, I think, but a profound, almost poetic demonstration of universal fine-tuning. It's a call to appreciate the miracle of existence because it was far, far from guaranteed.
And that profound personal connection is exactly what this deep dive is about. Our mission today is to explore exactly how we got from, as our sources so eloquently put it, nothing at all to something, and then how a little of that something turned into us. End quote. We're going to be pulling from a rich stack of sources that don't just tell us what scientists discovered, but vividly reveal how they did it, and introduce you to some of the remarkable, sometimes eccentric individuals behind these seemingly impossible breakthroughs. So our personal cosmic journey truly begins not with us, but with the universe itself. Let's rewind to the absolute beginning and explore how the very fabric of existence aligned perfectly for life, starting, of course, with the incredible story of the Big Bang.
Indeed. The universe, according to our most robust scientific understanding, emerged from what we might describe as nothing in a single blinding pulse. Now, this wasn't an explosion in the conventional sense, where something bursts into pre-existing space. Instead, it was a vast, sudden expansion of space itself on an utterly colossal scale.
A colossal expansion. To put that in perspective, our sources describe it as expanding to 1,000,000,000,000 billion miles across in less than a minute. That's roughly 100,000 times larger than our Milky Way galaxy is today, all within the time it takes for you to, I don't know, make a sandwich. It's a mind-boggling scale.
It is, and the speed and scale are difficult to grasp. In that first incredibly energetic second, the fundamental forces that govern everything, gravity, electromagnetism, and the strong and weak nuclear forces emerged. Then, within just 3 minutes, 98% of all the matter that exists or ever will exist in the universe had been produced. Primarily hydrogen and helium, the basic ingredients. We had, in essence, a newborn universe, almost ready-made in a way.
And here's where it gets really interesting, a surprising fact that you might already know without even realizing it. The next time you tune an old television to an untuned channel, about 1% of that dancing static you see is actually cosmic background radiation.
Right.
It's the ancient faint echo of the Big Bang itself, a literal relic from the birth of the universe. So what does this cosmic echo actually mean to us?
Well, it's a profound confirmation of the Big Bang theory. That faint microwave hiss is essentially the afterglow, the thermal signature of the universe when it was just about 380,000 years old. Before that, it was too hot and dense for light to travel freely. It was an opaque plasma. When it cooled enough, photons could finally escape, and those are the photons we detect today, stretched out into microwaves by the expansion of space. It tells us the universe started incredibly hot and dense and has been expanding and cooling ever since.
And much of our current detailed understanding of these unbelievably early moments of the universe comes from one individual's aha moment. Tell us about Alan Guth and his inflation theory. What was the core puzzle he was trying to solve?
Right, Alan Guth. He was a junior particle physicist at Stanford in 1979, only 32, and by his own account felt he had never done anything much before in terms of, groundbreaking work. He found his inspiration after attending a lecture on the Big Bang. The thing is, the standard Big Bang theory had a few persistent problems, like why does the universe appear so uniformly smooth on large scales? Why isn't it lumpier? And why is it so flat, meaning it's balanced perfectly between collapsing back on itself or expanding so fast that nothing could ever form?
Okay, so a lecture sparks this aha moment. Can you walk us through, even briefly, how Guth's theory of inflation offered a solution to some of the Big Bang's inherent puzzles and what made it so revolutionary?
Absolutely. Guth proposed that in the first tiny, tiny fraction of a second, we're talking 1/10 millionth of a trillionth of a trillionth of a trillionth of a second, an almost meaningless number, the universe underwent an incredibly rapid exponential expansion, a period he called inflation. This sudden, super fast stretch basically smoothed out any initial irregularities, like stretching a wrinkled balloon skin, which explains the uniformity we see. It also forced space into a perfectly flat geometry, solving that flatness problem. This instantaneous burst of expansion didn't just create vastness, it endowed the universe with the precise conditions needed for stability and structure formation later on.
The scale of that is almost impossible to grasp. But what's the core takeaway from Guth's inflation theory that fundamentally reshaped our understanding of the universe's origin?
The key insight isn't just the scale, but the incredible precision it implies. Our sources emphasize this. If gravity had been fractionally stronger or weaker, if that initial expansion had proceeded just a little more slowly or swiftly, then stable elements, and thus you and I and the ground we stand on, might never have existed. The universe would have either collapsed back in on itself like a badly erected tent, or it would have flown apart so quickly it remained just a dull, scattered void. Inflation theory showed us a universe that was, in a sense, pre-programmed for complexity, making your existence possible, but only within a very narrow, incredibly specific band of initial conditions.
Wow. Okay, from the infinitesimally small universe-defining moments, let's now consider its unimaginable scale. How did we move from a universe defined by fundamental forces to one where we could even begin to comprehend our own cosmic address?
The immensity is truly staggering. Current estimates suggest there are perhaps 140 billion galaxies in the visible universe, maybe more, each containing hundreds of billions of stars. Yet, incredibly, as recently as 1919, astronomers knew of only one galaxy, our own Milky Way. Everything else they saw in the night sky was thought to be either part of it or just distant puffs of gas nebulae within it.
It's hard to even picture that. One source mentioned an astrophysicist, Bruce Gregory, who calculated that if galaxies were frozen peas, they'd be enough to fill a huge auditorium like the old Boston Garden or the Royal Albert Hall. That really puts our perceived cosmic significance in a fascinating new light, doesn't it?
It truly does. And this dramatic expansion of our cosmic understanding began with some really crucial discoveries, often made by individuals whose contributions were, shall we say, initially overlooked. We absolutely have to highlight Henrietta Leavitt. She was one of Harvard's computers, a group of women employed, often for pretty low pay, to process astronomical data. She made a profound contribution by discovering Cepheid variables.
Okay, for our listeners, what exactly are Cepheid variables, and how did a pulsating star become a standard candle that could map the cosmos? What was the genius in that connection?
Cepheid variables are stars that pulsate, getting brighter and dimmer over a regular period. Leavitt's breakthrough was realizing that the brighter a Cepheid variable intrinsically was its actual wattage, if you like, the slower it pulsed. It's like finding a lighthouse where the flash rate tells you exactly how powerful its bulb is. Once you knew its true intrinsic brightness from its pulsation period, you could compare that to how bright it appeared from Earth. The difference instantly tells you how far away it is. It was an ingenious way to cut through cosmic distances, a cosmic yardstick, as our sources call it. Nothing like it existed before.
And this was at a time when other shall we say, more established male astronomers like William H. Pickering were busy publishing seminal theories that dark patches on the moon were caused by swarms of seasonally migrating insects. It really puts Leavitt's insightful foundational work into stark, almost humorous perspective.
It certainly does. Now, building on Leavitt's cosmic yardstick, and also the earlier observations of Vesto Slipher, who noticed that the light from distant spiral nebulae was often redshifted, Edwin Hubble truly revolutionized our understanding.
And just to make sure we're all on the same page, what exactly is redshift, and how did Slipher's observations of it, combined with Leavitt's work, become such a powerful tool for Hubble?
Right, redshift. It's like the Doppler effect for light. You know how an ambulance siren sounds higher-pitched coming towards you and lower-pitched going away? Light does something similar. If a light source is moving away from you, its light waves get stretched out, shifting towards the red end of the spectrum. The faster it moves away, the more its light shifts to red. Slipher saw these spiral nebulae were significantly redshifted, telling us they were moving away from us, and often very fast. Hubble then used Leavitt's Cepheids to get accurate distances to some of these nebulae. In 1923, he aimed the powerful Mount Wilson telescope at M31, the Andromeda Nebula, found Cepheids within it, calculated its distance, and demonstrated it wasn't a gas cloud within the Milky Way at all. It was a separate galaxy, 100,000 light-years across and at least 900,000 light-years away, vastly outside our own Milky Way.
So he didn't just find a galaxy. He essentially unlocked the reality of millions, maybe billions of them. And then he formulated Hubble's law.
Exactly. By 1924, he published a landmark paper showing the universe consisted of countless independent island universes, as they were called, galaxies. And his law, Hubble's law, formulated later, stated a clear relationship. Galaxies are flying away from us, and the farther away they are, the faster they're receding. This was conclusive evidence that the universe itself was expanding. It was a complete paradigm shift.
Wow. So what did Hubble's initial calculations tell us about the age of this expanding universe?
Well, that's where things got a bit tricky initially. Hubble's first calculation for the universe's age, based on his observed expansion rate, was about 2 billion years. This immediately presented a significant challenge because geologists and physicists already had strong evidence by the late 1920s that many things within the universe, not least the Earth itself, were likely much older than that.
No.
It highlights the ongoing iterative nature of science. No single discovery is the final word. Hubble's work was revolutionary, but the numbers needed refinement as measurement techniques improved. Science is a continuous process of observation, hypothesis, testing, and revision.
And we're talking about billions of galaxies, each with hundreds of billions of stars. This naturally leads to some fascinating speculation, doesn't it? About life beyond Earth.
It absolutely does. You can't contemplate those numbers without wondering. In the 1960s, Professor Frank Drake at Cornell famously developed an equation, the Drake equation, designed to estimate the number of detectable, technologically advanced civilizations in our galaxy. Even when you plug in pretty conservative numbers for the various factors, like the fraction of stars with planets, the fraction of planets that could support life, the fraction where life actually arises, and so on, the result always seems to come out somewhere in the millions, just in the Milky Way.
Millions. That's a mind-bending thought. So you, our listener, live in a cosmos far vaster, more dynamic, and potentially more populated than anyone could have imagined even a century ago. All thanks to these groundbreaking discoveries and the relentless curiosity of scientists. Now let's bring it a little closer to home, quite literally, with our next deep dive. Beneath our feet and around the sun, probing Earth's secrets. I want to start with a question I bet many of you have asked yourselves, just like I did when I was a kid.
Oh yes, it's that common childhood wonder, often sparked by a diagram in a textbook, isn't it? You see that cutaway of the Earth's interior showing these neat layers, crust, mantle, outer core, inner core, ending with this glowing sphere of iron and nickel, supposedly as hot as the surface of the sun. And you naturally ask, how do they know that? You can't exactly drill down there and take a look.
Exactly. I remember thinking it was some kind of, I don't know, ancient secret knowledge passed down through generations. But then I'd go to the textbook chapter, and it was all about anticlines and synclines and isostasy. Our sources mention how this often made science supremely dull and soberly unfathomable. It didn't answer the how. It felt like a universal conspiracy among textbook authors to keep the interesting stories secret.
It really highlights a fundamental gap in how science is often presented, focusing on the results rather than the process of discovery. Our deep dive today aims to bridge that gap, to answer precisely that how scientists work things out, often with incredible ingenuity and sometimes unbelievable perseverance, even when they couldn't directly observe what they were studying. How did they bring those diagrams to life?
And when we look at early Earth measurements, the ingenuity and sheer endurance of these early scientists is just astonishing. Let's start with Richard Norwood's epic walk.
Richard Norwood, right. An English mathematician in the early 17th century. He took on this monumental task of bringing mathematical rigor to navigation, which was still pretty haphazard. For 2 devoted years, he meticulously marched 208 miles from London to York, measuring every step with the chain, painstakingly adjusting for every dip and rise in the terrain, using sightings of the sun to keep his latitude precise. His goal: to calculate the length of a degree of Earth's meridian, basically, how big the Earth is. His final calculation, 110.72 kilometers per degree of arc, was accurate to within about 600 yards of modern figures. Just astounding precision for the time.
600 yards over 200 miles using a chain. That's incredible. And then there's a tale of the French expedition to Quito, a story of scientific ambition mixed with, well, absolute disaster.
The Quito expedition. A classic, almost legendary tale in the history of science. This team traveled halfway around the world, specifically to the equator in what is now Ecuador, to measure a degree of meridian using triangulation. Their rationale was that measuring near the equator, where the centrifugal force of Earth's spin was thought to make it bulge slightly, would help determine the precise shape of the planet. Was it perfectly spherical or slightly flattened like an orange?
And their journey was famously beset by pretty much every imaginable disaster.
Oh, indeed. Almost immediately, things went spectacularly wrong. Our sources recount how they provoked locals, their doctor was murdered in a misunderstanding over a woman, the expedition botanist went mad, another member ran off with a 13-year-old girl, crucial permits vanished mysteriously, and the two leaders, Condamine and Bouget, developed such an intense hatred for each other they stopped speaking for the remainder of the mission. Even local officials apparently found it hard to believe they would travel so far, enduring such hardship just to measure the world. Their perseverance, despite the chaos, speaks volumes about that early scientific spirit, or perhaps just sheer stubbornness.
And the obvious question arises, why on earth didn't they just measure it in France, where it would have been, well, significantly easier and less prone to disaster?
That's a great question. It highlights a certain 18th century scientific tendency, perhaps, to choose the most absurdly demanding alternative if it was available. But more seriously, measuring at the equator was scientifically important for determining the Earth's shape. This also connects to an even older pressing problem in navigation and astronomy, determining the scale of the solar system, specifically the distance from the Earth to the Sun. And that brings us to Edmund Halley.
Halley of comet fame. He seems to pop up everywhere in early science. He had an ingenious plan to measure the Earth-Sun distance, didn't he? Using Venus.
Yes, exactly. Halley realized long before it happened that transits of Venus, where Venus passes directly between the Sun and Earth, appearing as a small black dot crossing the Sun's face, could be used. These are rare events, coming in pairs 8 years apart, then maybe not again for over a century. Halley figured if you could precisely time the start and end of the transit from widely separated points on Earth, you could use simple trigonometry, the parallax effect, to calculate the distance to Venus, and from that, the distance to the Sun, the fundamental unit of the solar system. Though Halley didn't live to see the next transits in 1761 and 1769, his proposal galvanized the international scientific community. Scientists set off for over 100 locations globally, but many faced immense hardship.
And then there's the truly tragicomic ordeal of Guillaume le Gentil, who became almost a legend of scientific misfortune. Tell us his story.
Oh, Le Gentil. His story is one of monumental bad luck, coupled with unbelievable perseverance. He set off a year early for Pondicherry in India to observe the 1761 transit, but war between France and Britain meant he was still at sea on the crucial day, bobbing around on the Indian Ocean, making precise astronomical measurements impossible. Rather than return home defeated, he stoically decided to just wait in the region for the next transit, 8 years later in 1769. During this 8-year wait, he managed to map the coast of Madagascar, contracted dysentery, nearly shipwrecked. Finally, after 11.5 years away from home, he positioned himself perfectly in the Philippines for the 1769 transit, only for a freak cloud to obscure his view at the critical moment. Yes, he finally returned home to France to find his relatives had legally declared him dead and had enthusiastically plundered his estate. He achieved absolutely nothing scientifically from his epic voyage, yet his tale perfectly illustrates the incredible human cost and sometimes futile dedication behind these early scientific pursuits.
That's just heartbreaking. Utterly heartbreaking. But in contrast, Captain James Cook actually succeeded with the 1769 transit, didn't he?
Yes, thankfully someone did. Captain Cook, on his first great voyage of discovery, successfully observed the 1769 transit from Tahiti. His precise measurements, combined with others, provided enough data for the French astronomer Joseph Lalande to calculate the mean distance from the Earth to the Sun. His result was a little over 150 million kilometers. Further observations during 19th century transits refined this to 149.59 million kilometers. We now know the precise figure is 149.59787878691 million kilometers, or about 93 million miles. Thanks to these heroic efforts, often fraught with peril, the Earth finally had a precise position in space.
Amazing. And speaking of precision and figuring out fundamental properties of our planet, how on earth did anyone manage to weigh the Earth? This brings us to the eccentric brilliance of Henry Cavendish.
Henry Cavendish was, well, unique. A brilliant polymath, incredibly wealthy, but pathologically shy. So reclusive, he reportedly communicated with his female housekeeper primarily by letter, and once famously fled his own home by a back staircase when an admirer, a visiting Austrian scientist, tried to speak to him. Despite his extreme shyness, his scientific genius was undeniable. In 1797, he undertook this incredibly delicate year-long experiment involving 17 distinct, interconnected measurements to literally weigh the Earth. He set up an ingenious apparatus involving 2 large lead balls and 2 smaller ones, suspended on a torsion balance, basically a twisting wire. The minuscule gravitational attraction between the balls caused the wire to twist slightly. To avoid any disturbance, even from his own body heat or air currents, he observed the slight deflection of the wire through a telescope mounted outside the sealed room, peeking through a peephole.
The level of detail and patience required for that is just mind-blowing, observing through a peephole for a year. So what did he find?
His results were astonishingly accurate. Cavendish announced that the Earth weighed a little over 13 billion pounds, which translates to about 6 billion trillion metric tons. Modern measurements, with all our sophisticated technology, put the figure at 5.972 sextillion metric tons. His result was within 1% of the currently accepted value. What's truly remarkable, though, as our sources point out, is that this merely confirmed estimates made by Isaac Newton 110 years earlier purely through calculation without any experimental evidence at all.
Wow.
It just highlights this incredible blend of theoretical genius, meticulous experimental design, unwavering perseverance, and sometimes extreme personal sacrifice that went into establishing these foundational scientific facts we now take for granted.
So these seemingly simple facts about our planet are built upon centuries of extraordinary human endeavor, often by individuals pushing the absolute boundaries of what was thought possible. It's truly humbling. Let's transition now to the very ground beneath our feet and explore the dynamic planet. Plate tectonics. We're talking about the immense forces that shape continents and oceans, right?
Exactly. And our understanding of Earth's dynamics really began to take shape with James Hutton, often called the father of modern geology. He lived in the late 18th century and had these profound insights into the vastness of geological time and the slow, cyclical processes that shaped the Earth: erosion, deposition, uplift. But his writing style was notoriously difficult. Our source amusingly notes his prose was almost entirely innocent of rhetorical accomplishments. Luckily, his friend John Playfair, a professor of mathematics with a gift for clarity, rewrote Hutton's dense work into elegant, silken prose, making his revolutionary ideas accessible.
And geology really took off in the 19th century, right? It wasn't just for academics and ivory towers. It became almost popular.
Precisely. Our sources say it gripped the 19th century like no other science. The Geological Society of London, formed in 1807 by 13 like-minded individuals, began as essentially a dining club. But within a decade, its membership swelled to 400, attracting many gentlemen with the wealth and time to indulge a hobby at a more or less professional level. It became a fashionable pursuit. Apparently, even a detailed book on a specific type of rock called greywacke became a bestseller.
A bestseller about greywacke. That's a far cry from my dull science textbooks. Now, in geology, there was this big fundamental debate back then: catastrophism versus uniformitarianism. Can you unpack those for us? Why did it matter so much?
Right. This was a long-running central dispute. Catastrophists believed Earth's features were shaped primarily by sudden, violent, short-lived events, cataclysms like Noah's flood. This view is particularly comforting to many clerics, like the Reverend William Buckland at Oxford, as it allowed them to integrate biblical accounts with geological findings. Uniformitarians, by contrast, championed the idea that the geological changes we see are the result of slow, gradual, continuous processes acting over immense spans of time, the same processes we can observe happening today, like erosion and sedimentation. Hutton was the father of this idea, but it was Charles Lyell, in his influential book Principles of Geology, who really popularized it and ultimately convinced the scientific world. This shift to accepting deep time, millions upon millions of years, was absolutely crucial for understanding Earth's history and later for Darwin's theory of evolution.
But the idea of continents actually moving that was a truly radical notion, wasn't it? It seemed to fly in the face of all geological orthodoxy, even uniformitarianism to some extent.
It certainly did, and it came from a complete outsider. Alfred Wegener, a German meteorologist and Arctic explorer. In the early 20th century, his radical notions questioned the very foundations of geology. He proposed proposed that the continents had once been joined together in a supercontinent, which he later called Pangaea, and had subsequently drifted apart. He presented compelling evidence: the jigsaw puzzle fit of coastlines like South America and Africa, identical fossil distributions of land animals and plants found on widely separated continents, and geological formations like mountain ranges that seemed to line up perfectly when the continents were reassembled. However, he was largely dismissed, even ridiculed by the geological establishment, partly because he couldn't propose a convincing mechanism for how continents could plow through the solid ocean floor, and partly, let's be honest, because of professional prejudice. He was just a weatherman, an outsider trespassing on their turf.
And to counter his evidence, geologists just invented these phantom land bridges out of thin air, literally drawing them across oceans on maps.
Exactly. It seems almost comical now. When fossils of an ancient horse called Hipparion were found in both France and Florida, geologists drew a convenient land bridge across the Atlantic. For tapirs found only in South America and Southeast Asia, another bridge magically appeared across the Pacific. These hypothetical bridges conveniently rose and sank beneath the waves, leaving not so much as a grain of actual evidence behind. There was even an instance involving a specific trilobite species found only in Europe and the Pacific Northwest of North America, but nowhere in between. Our source dryly notes that explaining this required not so much a land bridge as a flyover. Yet this idea of static continents connected by ephemeral land bridges remained geological orthodoxy for nearly half a century, showing just how resistant established science can be to revolutionary new ideas, especially from outsiders.
That's wild. So who finally helped us understand the true mechanism of how continents could actually move? The how that Wegener was missing.
That crucial piece came from Arthur Holmes, a brilliant English geologist who also did pioneering work on using radioactivity to determine the Earth's age. Holmes was the first to really understand and champion the idea that radioactive decay deep within the Earth generates immense heat. This heat, he proposed, could create powerful convection currents in the underlying mantle, slow, circular movements of hot rock rising, cooling, and sinking, like in a pot of simmering stew. These currents, he suggested, could be powerful enough to literally drag the continents across the surface like rafts on a current. His 1944 textbook, Principles of Physical Geology, clearly laid out this mechanism, providing the theoretical foundation for modern plate tectonic theory. Though again, his ideas were still widely criticized or ignored, especially in the US, for decades.
And then, during World War II, the ocean floor started giving up its secrets, almost accidentally, revealing features that perfectly matched Holmes's and Hess's ideas.
Yes, that's a fascinating part of the story. Harry Hess, a mineralogist from Princeton, was commanding an attack transport ship during the war. Naval vessels were newly equipped with depth sounders or fathometers, primarily for detecting enemy submarines. Hess, being a geologist, kept his fathometer running constantly as his ship crisscrossed the Pacific. He discovered that the ocean floor was not the flat, featureless, sediment-covered plain everyone assumed it to be. Instead, it was incredibly dynamic, scored everywhere with canyons, trenches, and crevasses, and dotted with volcanic seamounts, including flat-topped ones he named guyotts. After the war, extensive mapping by oceanographic institutions revealed the truly astounding topography of the seabed, including the mightiest and most extensive mountain range on Earth, the mid-ocean ridges, vast volcanic chains snaking for 40,000 miles beneath the waves. This was where new ocean floor was being created, pushing the continents apart.
An entire hidden landscape, completely unknown. And then there's Earth's magnetic memory locked away in rocks, providing another crucial piece of the puzzle.
Right, this is where different lines of evidence start converging beautifully. Back in 1906, a French physicist named Bernard Brunis discovered that some rocks were magnetized opposite to the Earth's current magnetic field. He correctly inferred that Earth's magnetic field must reverse its polarity periodically. Later, scientists realized that as volcanic rocks cool and solidify, tiny magnetic mineral grains within them align themselves with the Earth's magnetic field at that specific time, like tiny fossil compasses locking in a record of the field's direction. In the 1950s, Patrick Blackett and S.K. Runcorn at Cambridge studied these ancient magnetic alignments, paleomagnetism, in rocks from different continents and different ages. They found, for instance, that ancient British rocks pointed to a North Pole located somewhere near Hawaii, indicating Britain had drifted and rotated over geological time. Even more compellingly, they found that the paths of apparent polar wandering recorded in European rocks and North American rocks only make sense if the two continents had once been joined together and had subsequently drifted apart. The patterns fit together as neatly as two halves of a torn letter.
That's an incredible piece of converging evidence, almost like finding matching fingerprints. And the definitive proof that tied it all together, that really confirmed seafloor spreading and continental motion, came in 1963, didn't it? The Vine-Matthews hypothesis.
Yes, that was the final, clinching piece. It finally fell to Drummond Matthews and his graduate student Fred Vine, also from Cambridge. They were studying magnetic surveys of the Atlantic Ocean floor around the mid-ocean ridge. They noticed a striking pattern: stripes of normal and reverse magnetism mirrored symmetrically on either side of the ridge. They realized this was the pattern you'd expect if new volcanic rock was constantly forming at the ridge, recording the Earth's magnetic field polarity at the time of its creation, and then being pushed sideways like a giant magnetic tape recorder. This demonstrated conclusively seafloor spreading, confirming Hess's ideas about new crust forming at ridges and providing the missing engine for Wegener's continental drift. Sadly, there's a poignant footnote. An unlucky Canadian geologist named Lawrence Morley came to the exact same conclusion independently around the same time, but couldn't get his paper published. The prestigious Journal of Geophysical Research rejected it, with the editor famously telling him, "Such speculations make interesting talk at cocktail parties, but it is not the sort of thing that ought to be published under serious scientific aegis."
Ouch. That's brutal.
It's been called probably the most significant paper in the earth sciences ever to be denied publication. Real shame for Morley, and a stark reminder of the sometimes arbitrary nature of scientific recognition.
Wow. Poor Morley.
Yeah.
So what does this constant tearing apart and stitching back together of our planet, this dynamic process of plate tectonics, mean for us? Why is it so important for life?
Well, Earth is apparently unique among the rocky planets in our solar system in having active plate tectonics, and its importance for life is absolutely profound. You have to think of the Earth's surface not as a solid, static shell, but as a mosaic of constantly moving plates like cracked pieces of an eggshell floating on the slowly turning, viscous mantle beneath. The heat from radioactive decay deep within drives these immense convection currents in the mantle, and those currents literally drag the continents around, tear oceans open, crash land masses together to build mountains, trigger earthquakes and volcanoes. James Trifle, a physicist, suggests that the very challenges posed by tectonic shifting climates as continents drift, the creation of new habitats and environmental stresses, might have been an important spur to the development of intelligence. And oceanographer Tony Dixon's work connects major shifts in ocean chemistry, driven by tectonic activity like volcanism at mid-ocean ridges, with key events in biological history, like the huge outburst of tiny organisms, coccolithophores, that created the chalk cliffs of England's south coast. Essentially, you live on a planet that is constantly recycling its crust, regulating its climate, and creating diverse environments, all thanks to this internal heat engine. It's a process absolutely essential for maintaining the conditions necessary for complex life, for your very existence.
But tectonics, as powerful and unifying as it is, doesn't explain absolutely everything we see on the surface, does it? There's still some nagging geological mysteries.
That's a very important point. Science rarely provides complete answers. It's crucial to acknowledge what we still don't fully understand. Tectonics, for instance, doesn't easily explain why Denver, Colorado, which sits on ancient continental crust that was once part of an ocean bottom, has somehow risen a mile high without any obvious nearby plate collision or crustal fracturing. Our source says it rose gently and persistently like baking bread. Nor does standard tectonic theory readily account for why southern Africa has risen by nearly a mile over the last 100 million years, or why Australia seems to be tilting and sinking along its northern edge as it drifts northwards. As our sources state, nothing in the theories of tectonics can explain any of this. These anomalies remind us that our planet still holds deep secrets, and there's always more to learn.
Right. Always more questions. And speaking of what we still don't fully understand, let's talk briefly about Earth's fiery core and the magnetic shield it generates. How much do we really know about what's deep, deep beneath us, given we can't physically go there?
We know surprisingly little, in some ways. It's quite remarkable, as one source notes, that humans were building cars and playing in the World Series for decades before we even knew for sure that Earth had a core. Through analyzing seismic waves from earthquakes as they travel through the planet, scientists have deduced the basic structure: a relatively thin, rocky outer crust, a very thick, viscous mantle, a liquid outer core, and a solid inner core. The overall density of the planet, calculated by Cavendish, and the presence of our vital magnetic field strongly imply that the core must be composed primarily of metallic elements, mostly iron and nickel, with the liquid outer core circulating and generating the field through a dynamo effect.
But the mantle, which makes up this huge percentage of the Earth's volume, is still largely ignored and mysterious in many ways.
That's right. The mantle accounts for a staggering 82% of Earth's volume and about 65% of its mass. Yet it's often largely ignored in popular depictions, and even scientifically, much about its deeper structure and dynamics remains uncertain. We know the upper mantle, down to a few hundred miles, consists predominantly of a rock called peridotite. But what lies beneath, how the convection currents really operate, is still debated. As physicist James Trefil candidly put it, the embarrassing fact is that we understand the distribution of matter in the interior of the sun far better than we understand the interior of the Earth. It's a vast frontier of the unknown right beneath our feet.
And this mysterious internal engine also gives us our crucial magnetic field, which isn't static either. It's constantly changing, sometimes quite dramatically.
Exactly. The magnetic field fluctuates in strength. Sometimes it's been perhaps 3 times as strong as it is now, other times much weaker. But most dramatically, as Bryn has discovered, it reverses its polarity altogether. North becomes south, south becomes north. On average, this happens roughly every 500,000 years, but that's just a long-term average. It's highly unpredictable. The last full reversal was about 750,000 years ago. But sometimes the field stays stable for tens of millions of years. 37 million years is the longest known stable period, and at other times it's flipped after as little as 20,000 years. In the last 100 million years alone, it's reversed about 200 times. And we truly have no real idea why this happens or exactly how the reversal process initiates and unfolds. It's been called the greatest unanswered question in the geological sciences.
So what does this fluctuating, reversing, and partially mysterious magnetic field mean for us, the listeners, and our very survival on this planet?
Your very survival, in many ways, depends on this unseen, dynamic, and still somewhat mysterious internal engine. The magnetic field acts like a giant shield, deflecting most of the harmful charged particles from the solar wind and cosmic rays that would otherwise bombard the surface, strip away our atmosphere over time, and make complex life largely impossible. Without it, the challenges for life on the surface would be far, far more extreme. So while we can marvel at its protective effects, the intricate mechanics churning away deep beneath our feet remain a tantalizing frontier of discovery, a testament to how much we still have to learn about our own home planet.
Okay, we've journeyed from the Big Bang to the Earth's fiery core. Now let's embark on our final, perhaps most intimate deep dive. Life's extraordinary journey, from cells to sentience. And it all begins with the sheer improbable miracle of life itself at the level of molecules.
Indeed. When you look at the fundamental building blocks of life, like proteins, they are incredibly complex arrangements of simpler units called amino acids. Our sources describe them like words made of letters, but exceedingly long and specific words. To make just one common protein, collagen, the stuff that holds your skin together, you need to arrange 1,055 amino acids in precisely the right sequence. The number of possible incorrect sequences is astronomical. Yet the astonishing part, the miracle our source refers to, is that these incredibly complex functional structures somehow make themselves spontaneously, without direction, folding into the correct shapes to do their jobs. The origin of this informational complexity remains one of the deepest questions.
That's a profound thought. So how did such complexity arise without any apparent external guidance? And it's not just the proteins themselves, but the cell, the container that's crucial, acting as a refuge for life, right?
That's the core issue. No single atom or molecule is alive on its own. Life, as we know it, happens when a whole diverse collection of complex molecules and materials come together and are contained within the nurturing, protective refuge of a cell membrane. The physicist Paul Davies used a wonderful analogy cited in our source. Imagine all the ingredients in your kitchen somehow got together and baked themselves into a cake, but a cake that could moreover divide when necessary. That membrane is absolutely crucial. It concentrates the necessary chemicals, protects the delicate molecular machinery inside from the outside world, maintains the specific internal chemical environment needed for life's reactions, and controls what comes in and goes out.
And who first gave these tiny fundamental units of life their name? Who first glimpsed this hidden world?
That would be the brilliant, versatile English scientist Robert Hooke, whom we encountered earlier regarding geology as well. In 1665, in his hugely popular and beautifully illustrated book Micrographia, he described looking at thin slices of cork under his microscope. He saw a structure of tiny, empty boxes or pores, which reminded him of the small rooms, or cells, where monks lived in monasteries, and so he called them cells. His microscope achieved about 30x magnification, which was state-of-the-art for the mid-17th century. He even calculated that a 1-inch square of cork would contain over 1.2 billion of these tiny chambers, a truly staggering number for people to conceive of back then.
But then, just a decade later, an unlettered linen draper in Holland, Antony van Leeuwenhoek, completely blew Hooke's technology out of the water.
Yes, Antony van Leeuwenhoek is one of the great unsung heroes of biology. He was a draper, basically a cloth merchant in Delft, with little formal scientific education, but he was a technical genius at grinding tiny, powerful lenses. He crafted these simple, single-lens, handheld microscopes, keeping his technique secret, that achieved magnifications of up to 275 times, far surpassing anything else available. With these, he was the first human to see bacteria, protozoa, sperm cells, blood cells flowing through capillaries, a whole hidden world of animalcules, as he called them. His fantastic findings sometimes led others down strange paths, like Nicholas Hartsoker, imagining he saw tiny preformed men, or homunculi, curled up inside sperm cells.
And it's a little human idea.
A naive but perhaps understandable early interpretation. Leeuwenhoek himself was apparently almost blinded trying to study the explosive properties of gunpowder at close range under his lens. His revolutionary work truly opened the door to the microscopic world, the world where your very existence resides.
So what do we know about the fundamental structure of these cells that make up every part of you? What's the basic plan?
Well, nearly all the cells in your body share a fundamental plan. There's an outer boundary, the cell membrane, a central compartment, the nucleus, which holds the genetic information, your DNA, and then the jelly-like substance filling the space in between called the cytoplasm, where most of the cell's work gets done. Now, the membrane isn't a tough, rigid casing like a wall, as you might imagine. It's primarily made of fatty molecules called lipids, and our source says it has the consistency of light grade of machine oil. It's fluid, flexible, but perspective matters. At the incredibly tiny molecular level, things behave differently. Water inside a cell isn't like water in a glass. It acts more like a heavy-duty gel because of all the dissolved molecules. And to a molecule trying to get through it, that lipid membrane feels like iron. This emphasizes how radically different the microscopic world is from our everyday macroscopic experience. That specific fluidity and selective permeability of the membrane are crucial. It acts as the perfect gatekeeper and container for life's intricate chemical reactions. Each of your estimated 10,000 trillion cells is like a loyal, complex citizen, constantly working in concert to preserve and nurture the whole organism you.
It's astounding to think about that hidden, microscopic city constantly at work within us. Thousands of trillions of loyal citizens. Now let's zoom back out and consider Earth's grand transformation, particularly the role of oxygen and the dramatic Cambrian explosion. What was early Earth like before oxygen became abundant, and how did life manage?
The Archean world, say 3 billion years ago, was an ancient Earth you wouldn't recognize, as our source puts it. There was essentially no free oxygen in the atmosphere or oceans. Instead, the atmosphere was likely rich in gases like methane, ammonia, carbon dioxide, and maybe noxious vapors like hydrochloric and sulfuric acids from intense volcanic activity. And the sun was significantly dimmer back then, maybe 20–30% less luminous than today. So very little sunlight, especially filtering through that hazy atmosphere, reached the surface. Biologists even joke about the Chinese restaurant problem for early life because it had a dim sum, very little available energy from sunlight at the surface. It was an Earth utterly unsuited for complex, oxygen-breathing life as we know it.
So who started cleaning up this noxious mess and making the oxygen that eventually allowed us to evolve?
The heroes of this story are tiny microbes called cyanobacteria, also known sometimes as blue-green algae. They evolved the remarkable trick of photosynthesis using sunlight, water, and carbon dioxide to make energy, and releasing oxygen as a waste product. But this oxygen didn't immediately build up in the atmosphere. For maybe 1 billion years or more, it reacted with abundant dissolved iron in the oceans. The iron effectively rusted out of the water, forming iron oxides that settled on the seabed. This process created the massive geological formations known as banded iron deposits, which are the source of most of the iron ore we mine today, the very stuff our modern civilization is built on. So, for millions upon millions of years, the world quite literally rusted thanks to these tiny organisms. It was a planetary-scale geoengineering project carried out by microbes.
Wow. The world rusted for 1 billion years. And then after about 2 billion years of relatively simple, mostly single-celled life, and once most of the iron was used up, oxygen levels finally started to rise in the atmosphere and oceans. And something dramatic happened. The Cambrian explosion. What was this sudden burst of complex life, and why was it so important?
Yes, after these vast stretches of time dominated by microbes, oxygen levels finally rose sufficiently to support larger, more energy-intensive life forms. Then, geologically speaking, quite suddenly over a period of perhaps just 5 to 10 million years, around 540 million years ago, there was this incredible burst of evolutionary innovation. Almost all the major animal body plans, the basic blueprints or phyla that exist today, appeared in the fossil record during this relatively short window. As our source humorously puts it, name a creature, from a nematode worm to Cameron Diaz, and they all use architecture first created in the Cambrian party. Arthropods with exoskeletons, mollusks with shells, chordates with primitive backbones. The foundations for virtually all complex animal life were laid down in this evolutionary frenzy.
So a sudden dramatic burst of complex life. But wasn't there a life before that party started? What about the Ediacaran fauna? These strange, delicate creatures predated the Cambrian explosion, right?
They did, yes. Starting in the 1940s, fossils of strange, soft-bodied organisms were found in rocks slightly older than the Cambrian, most famously by Reginald Sprague in the Ediacaran Hills of South Australia. These Ediacaran creatures were quite unlike anything that came later. They looked like quilted mats, fronds, discs, things with no obvious heads, mouths, or limbs. For a long time, their significance was debated. Sprague's initial findings were even dismissed at an International Geological Congress as just fortuitous inorganic markings. Patterns made by wind or rain, maybe jellyfish impressions, but not remnants of actual complex organisms. Many authorities, like paleontologist Richard Fortey, believe these Ediacaran creatures weren't terribly important to the later development of life. It's thought there might have been a mass extinction event at the boundary between the Precambrian and Cambrian periods that wiped out most of these early experiments in multicellularity, meaning the real business of complex life, the ancestors of today's animals, largely started anew with the Cambrian explosion.
Okay, so it was a sudden explosion then, or has that view been perhaps reappraised? Are scientists finding a more nuanced story now? Did it all really appear out of nowhere?
Scientific understanding is always evolving, and the explosion concept is a great example of that ongoing refinement. While the appearance of large, skeletonized fossils is quite abrupt in the record, scientists like Richard Fortey and Derek Briggs, using techniques like cladistics, which groups organisms based on shared evolutionary features, have suggested that the Cambrian animals weren't as strange and various as paleontologist Stephen Jay Gould had argued in his famous book Wonderful Life. They proposed that the explosion might appear more sudden than it really was because the ancestors of the Cambrian groups were likely small, soft-bodied, and simply didn't fossilize well. The fuse to the explosion might have been burning slowly for tens of millions of years before the Cambrian, but only when creatures evolved hard shells and skeletons did they start leaving a prominent fossil record. The fact that different types of complex animals, like various trilobites, seem to appear almost simultaneously in widely scattered locations around the globe right at the start of the Cambrian strongly suggests a missing history, smaller, earlier ancestors that simply left no trace. Think about the seas today. They swarm with tiny arthropods like copepods that leave virtually no fossil record. It's not hard to imagine early animal life being similarly ephemeral in the fossil record.
That's a really good point. Small, squishy things are hard to preserve over millions of years. So the very air you breathe, oxygenated by ancient microbes, the complex body plan you inhabit, first sketched out during that Cambrian diversification, all of it traces back to these ancient dramatic shifts and the ongoing scientific debates trying to piece together life's deep history.
Precisely. It's a testament to the immense stretches of time, the profound environmental changes driven by geology and biology, and the power of evolution to shape the astonishing biodiversity we see around us and are still discovering today.
Now let's explore the unpredictable path to humanity. This part of our story involves two absolute giants of biology, Charles Darwin and Gregor Mendel. Their individual breakthroughs, though initially unconnected, ultimately fused to form the foundation of modern life sciences.
Charles Darwin, of course, with his theory of evolution by natural selection, laid the groundwork. His key idea was descent with modification, life changes over generations. Interestingly, our sources note that the famous phrase survival of the fittest wasn't actually Darwin's. It was coined later by the philosopher Herbert Spencer. And while the finches of the Galapagos are iconic, they weren't his initial aha moment either. Rather, it was the broader patterns of adaptation and distribution he observed during his voyage on the Beagle. It's also crucial to remember Alfred Russel Wallace, who independently conceived of natural selection around the same time, prompting Darwin to finally publish his own long-researched ideas.
And then, working completely separately, about 800 miles away in quiet seclusion in what's now the Czech Republic, Gregor Mendel was independently working out the actual mechanism of inheritance, the rules of heredity, even though Darwin never knew about it or its significance.
Mendel's story is fascinating. He was indeed a retiring monk at a monastery in Brno, but he was far from being just a simple gardener tinkering with plants, as sometimes portrayed. He was actually a trained scientist, having studied physics and mathematics at the University of Vienna. His meticulous quantitative experiments breeding pea plants over 8 years established the existence of discrete hereditary units, factors, he called them, which we now call genes that are passed down from parents to offspring according to predictable rules. He identified dominant and recessive traits and formulated precise mathematical ratios for how these traits appear in subsequent generations. His groundbreaking work, though published in 1866 in a respectable but obscure journal, and even mentioned in a paper that Darwin apparently read but didn't grasp the significance of, was largely ignored by the scientific community for over 3 decades. It was only rediscovered around 1900. When Mendel's laws of inheritance were finally combined with Darwin's theory of natural selection in the early 20th century, it formed what biologists call the modern synthesis, the powerful framework that has underpinned life sciences ever since.
It's incredible to think how much faster science might have progressed if they had somehow connected, or if Darwin, who struggled with understanding heredity, had recognized the significance of Mendel's mathematical approach. It's a poignant reminder of how scientific progress can sometimes be fragmented, delayed by lack of communication or recognition.
It truly is. But together, often posthumously, these two brilliant minds revolutionized our understanding of life itself, connecting the grand sweep of evolutionary change over millennia with the precise microscopic mechanisms of how traits are passed from one generation to the next.
And when it comes to tracing our own specific evolutionary path, the human fossil record is surprisingly sparse, isn't it? Given how intensely interested we are in our ancestors.
It is remarkably sparse, disturbingly so, perhaps. Ian Tattersall, a leading paleoanthropologist at the American Museum of Natural History, is quoted in our sources noting that the total world archive of known hominid fossil bones could literally fit into the back of a single school bus. Even for a species like Homo erectus, which existed for over 1 million years, far, far longer than our own species has been around and spread across Africa and Asia, Tattersall reckons all the known fossil individuals could also probably fit in that same bus if they were brought back to life. It really puts into perspective how little physical evidence we actually have to work with when reconstructing our deep past. And it makes you think how easily a civilization as relatively short-lived as ours could vanish, leaving virtually no trace in the fossil record millions of years from now.
That's a tiny amount of evidence, really, yet paleoanthropologists seem to get into these huge, often quite heated debates over the interpretation of these few precious fragments.
Well, yes. It highlights a fascinating and sometimes problematic human element in scientific interpretation. Our sources point out that scientists, being human, sometimes have a natural tendency to interpret new finds in ways that flatter their stature or confirm their pre-existing hypotheses or perhaps secure more funding. As science writer John Reeder observed, it is remarkable how often the first interpretations of new evidence have confirmed the preconceptions of its discoverer. The field of paleoanthropology, dealing with our own origins, is particularly known for its strong personalities and sometimes intense egos, leading to significant debates over things like, famously, how Lucy walked.
Speaking of Lucy, there's been a lot of debate about whether she walked upright, just like modern humans.
Right.
Was she fully bipedal in our sense?
Indeed. Lucy, the famous Australopithecus afarensis fossil discovered by Donald Johanson in Ethiopia in the 1970s, sparked huge debate. Johanson and his camp argued strongly that her skeletal anatomy, particularly her pelvis and knee joint, indicated she walked fully upright, much like us. Others, however, like Ian Tattersall, strongly disagree. They point to features like her long, curved fingers and toes and shoulder joints adapted for climbing, insisting Lucy and her kind did not locomote in anything like the modern human fashion. Their view is that afarensis was likely capable of upright walking, perhaps when moving between trees or across open ground for short distances, but still spent significant time in trees and retained many arboreal adaptations. The debate continues.
And the new discoveries keep complicating our family tree, making it even more fascinating and definitely less like a simple straight line.
Absolutely. The picture gets richer and messier all the time. In recent decades, finds like Kenyanthropus platyops from Kenya, Ardipithecus ramidus kadaba from Ethiopia, Ornithogenensis from Kenya, nicknamed Millennium Man, and especially Sahelanthropus chidensis from Chad, known as Tumai. These have pushed back the evidence for habitual upright walking much, much earlier than previously thought, some dating back almost 7 million years ago, very close to the estimated split from the chimpanzee lineage. This continually reshapes our understanding of our earliest ancestors and strongly suggests our family tree isn't a neat ladder of progress at all, but far more complex, a dense, tangled bush with many parallel branches, side shoots, and probably evolutionary dead ends. It's much more intricate than the simple linear progression we often like to imagine.
This brings us to a really interesting, and as our source calls it, deeply puzzling mystery. The toolmaker's mystery, specifically concerning the Acheulean hand axe. What makes this particular tool so perplexing?
Right, the Acheulean hand axe. About 1.5 million years ago, some unknown, forgotten hominid genius, likely a member of Homo erectus or a related species, created the first piece of truly advanced standardized technology. This beautifully crafted, symmetrical, teardrop-shaped stone tool. These hand axes were remarkably uniform in design across vast distances and time spans, incredibly sophisticated to make compared to earlier, simpler stone tools, and they were produced in huge numbers in the thousands, found at many sites. Their exact function isn't always clear. Some seem too large or unwieldy for butchery, leading Ian Tattersall to speculate they were perhaps sometimes made for the sheer pleasure of it as displays of skill or social status. But the deep puzzle is their geographical distribution. While these signature Acheulean tools are found abundantly throughout Africa, the Middle East, Europe, and West and Central Asia, they are almost never found in the far east of the Indian subcontinent. Early humans were certainly present in East Asia, but they seem to use different, perhaps simpler toolkits, often based on bamboo, which doesn't preserve.
That's a huge geographical discrepancy, a technological dividing line almost. Why is that? What does it imply?
That's the million-dollar question that continues to puzzle paleoanthropologists. It suggests something fundamental was different about the early human populations or their environments east of what's sometimes called the Mobius line. Did different groups simply develop entirely different technological traditions based on available materials? Was there some kind of cognitive difference? Or was there perhaps a geographical or environmental barrier that prevented the spread of this specific, rather complex Acheulean tool-making technique eastward? Or did the Eastern groups lose the technology? It's a tantalizing unsolved mystery about the cognitive abilities, cultural transmission, and migration patterns of our early ancestors.
Fascinating. Now, let's jump across the ocean to Australia. The evidence for early human inhabitants there really pushes back arrival dates significantly, doesn't it? And suggests incredible, almost unbelievable navigational feats for the time.
It really does. Human skeletal remains found at Lake Mungo in southeastern Australia were reliably dated back to around 60,000 years ago, with stone tools and other signs of occupation nearby going back perhaps even further. This was astounding because Australia has always been separated from Southeast Asia by significant stretches of open ocean, even during ice ages when sea levels were lower. To get there, these earlier modern humans must have made deliberate sea crossings, likely using rafts or simple boats covering distances of over 60 miles, 100 kilometers or more, island hopping perhaps, but eventually crossing deep water without knowing for sure if land awaited them on the other side. And then, once arrived, they managed to penetrate 2,000 miles inland to places like Lake Mungo relatively quickly. This implies human arrival in Australia must have occurred substantially earlier than 60,000 years ago, demonstrating an astonishing level of planning, ingenuity, risk-taking, and seafaring capability much earlier than previously credited to our species.
Incredible journeys. And then there are closest extinct relatives, the Neanderthals. Their story, or rather our understanding of them, has been completely reassessed, hasn't it? From brutish cavemen to something much more complex.
Absolutely. For a long time, Neanderthals were the archetypal cavemen depicted in illustrations and museum dioramas as dim, stooped, shuffling, and simian. This image largely stemmed from the initial reconstruction of the first relatively complete Neanderthal skeleton found at La Chapelle-aux-Saints in France, which happened to belong to an old individual suffering from severe arthritis. However, our sources recount a telling anecdote. In 1947, a French paleontologist named Camille Ehrenberg suffered a painful accident involving a burst airplane tire that injured his neck. When he later saw an X-ray of his own neck vertebrae, he had a revelation. They looked remarkably similar to the supposedly simian stooped vertebrae of the La Chapelle Neanderthal he had studied. He realized the Neanderthal's posture had been misinterpreted due to pathology, not inherent primitiveness. His own vertebrae weren't simian, and neither were the Neanderthals. This realization, though slow to permeate, changed utterly how we viewed Neanderthals, helping to dismantle the old stereotype.
So their posture was simply misunderstood due to arthritis in one key specimen. But the debate about their capabilities didn't end there, did it? Especially considering their brains were actually, on average, larger than ours.
Yes, that's a fascinating point. Neanderthals had significantly larger cranial capacities, averaging around 1.8 liters compared to the modern human average of about 1.4 liters. The argument is often made that perhaps our smaller brains were somehow wired more efficiently, but as our sources point out, such an argument that smaller is better is nowhere else invoked in human evolution. Usually, bigger brains are seen as an advantage. The evidence now shows Neanderthals were highly skilled toolmakers with their own distinct Mousterian technology. Effective hunters, likely used fire, probably buried their dead, possibly had some form of language, and were magnificently resilient. They survived and thrived across a vast territory from Europe to Central Asia for at least 100,000 years and during brutal Ice Age conditions. They were clearly highly adaptable and intelligent human relatives. Why they eventually disappeared while Homo sapiens survived remains a complex and hotly debated topic. Climate change, competition, disease, perhaps interbreeding and assimilation all likely play roles.
And finally, moving into the modern era of study, the DNA puzzle. Genetics helps us trace our lineage, but also throws up anomalous clusters, adding even more complexity to the human story.
Right. Genetics has revolutionized paleoanthropology. We know that on average, any two humans share about 99.9% of their DNA sequence. That tiny 0.1% difference, mostly due to variations at single points in the DNA code called single nucleotide polymorphisms, or SNPs, accounts for all human diversity. What's crucial to understand, as our source emphasizes, is that because of this variation, there is no such thing as the human genome. Every individual's genome is unique, a mosaic inherited from their ancestors.
And the patterns in this genetic variation generally support the out-of-Africa hypothesis for the origin of modern humans. But it's not a perfectly clean, straightforward story, is it? There seem to be some unexpected twists.
Exactly. While the bulk of genetic evidence strongly supports the model that modern humans originated in Africa relatively recently, within the last 200,000 years or so, and then migrated out to replace or interact with other archaic human populations like Neanderthals, it's not quite that simple. Biological anthropologist Rosalind Harding notes that while out of Africa is probably 95% correct, there are certain anomalous clusters in the genetic data, particularly in Asia, that are harder to explain with a single simple dispersal model and might suggest more complex scenarios. She suggests that things are likely to turn out to be not so straightforward, with evidence potentially pointing towards multiple migrations and dispersals in different parts of the world, going in all kinds of directions and generally mixing up the gene pool. We now know, for instance, from ancient DNA extracted from fossils that there was interbreeding between migrating modern humans and Neanderthals, and also with another archaic group called Denisovans found in Asia. So the picture is definitely one of complex interactions in gene flow, not just simple replacement. And extracting and analyzing ancient DNA is itself fraught with difficulty. The risk of contamination from modern human DNA from excavators, lab technicians, even just breathing on a bone is enormous, making interpretation challenging.
So your lineage, our collective human lineage, is truly a complex, interwoven tapestry full of twists, turns, migrations, interactions, and ongoing scientific detective work. It's certainly not as clean and linear as we might sometimes wish, but perhaps all the more fascinating and, well, human for it.
Absolutely. We've really only just begun to fully map the intricate routes and intersections of our genetic highways, and every new fossil find, every ancient genome sequenced adds another complex, often surprising thread to that tapestry.
Okay, to wrap up our epic journey today, let's look briefly at the ongoing quest, what we still don't know. Because despite all these incredible discoveries spanning billions of years, there's still an almost unimaginable amount of life right here on Earth that we haven't even cataloged, let alone understood.
It's truly astounding just how much unseen life surrounds us, and even lives within the Earth itself. Our sources mention that if you scoop up just a handful of ordinary garden soil, you'll be holding billions of bacteria, millions of yeasts and other fungi, hundreds of thousands of protozoans, the vast majority of them completely unknown to science, never cultured or named. Physicist Thomas Gold of Cornell even estimated, perhaps speculatively but provocatively, that the total biomass of microbial life living deep within the Earth's crust could exceed all the life on the surface. He suggested if you took all these deep Earth bacteria and dumped them on the surface, they might cover the entire planet to a depth of 5 feet. Some of this deep life might be incredibly slow living, dividing perhaps only once a century or even once every 500 years. It's a vast hidden biosphere we're only beginning to explore.
That's astounding. A 5-foot layer of unknown bacteria. We're literally standing on, or perhaps in the hidden world, teeming with unknown life. And this naturally leads to what our sources call a taxonomist crisis, doesn't it? We simply can't keep up with naming and describing all the life that's out there.
It's a serious problem. Taxonomy, the science of identifying, naming, and classifying organisms, is fundamental to understanding biodiversity, but it's critically underfunded and understaffed. There are maybe only about 10,000 truly active expert taxonomists globally across all groups of life. It takes 8 to 10 years of specialized training to become proficient, but jobs and funding are scarce. Cone Mays, head of invertebrates at the Kenyan National Museum, is quoted declaring, "It's not a biodiversity crisis, it's a taxonomist crisis." The All Species Foundation estimated some years ago it could cost anywhere from $2 billion to maybe $50 billion to find and describe all the species on Earth. At the current rate of discovery and description, cataloging just the insects alone could take something like 15,000 years. We're almost certainly losing species to extinction faster than we can even identify them.
So we have all this unseen microbial life and potentially millions of undiscovered insects and other creatures, and not enough people to even find them, let alone understand their roles in ecosystems. But we're also still discovering surprisingly large, hidden animals and incredible examples of extreme survival, even in the 20th and 21st centuries.
The world definitely still holds biological surprises, even for larger animals. The okapi, that striking relative of the giraffe with striped legs, was only formally described by science in the early 20th century, discovered in the dense forests of what is now the Democratic Republic of Congo. The takahe, a large flightless bird in New Zealand, was thought to be extinct for decades until it was dramatically rediscovered in a remote mountain valley in 1948. And as recently as 1995, a scientific team exploring a remote valley in Tibet, lost in a snowstorm, stumbled upon herds of the Riwash horse, a primitive-looking breed previously known only from prehistoric cave paintings in France.
Wow, finding a cave painting horse alive. And then there are microscopic creatures like the beadloid rotifers, which seem almost indestructible, capable of surviving conditions that would kill almost anything else.
Beetloid rotifers are truly remarkable. These microscopic aquatic animals, often found in temporary puddles or mosses, have this incredible ability to survive complete drying out and also extremes of temperature. They can apparently survive being boiled or frozen to near absolute zero. When conditions improve, they just rehydrate, uncurl, and carry on as if nothing happened. They also reproduce entirely asexually, which is very unusual for animals. Only about 500 species have been identified worldwide, largely thanks to the lifelong dedication of a single amateur British naturalist named David Bryce in the early 20th century. But we have almost no idea how many more species exist or how they manage these incredible feats of survival. They exemplify the sheer tenacity and resilience of life in unexpected corners.
It really drives home the point made in our source. Life just wants to be, and often, for the most part, it doesn't want to be much. Like lichens, those composite organisms of fungi and algae, thriving on bare rock in the harshest deserts or highest mountains, seemingly content just to exist, enduring any insult for a moment's additional existence.
Exactly. It prompts us to maybe reconsider our often human-centric view of purpose and ambition. While we strive and plan, much of life on Earth simply is persisting, adapting, surviving against incredible odds. Lichens are a perfect example. They remind us that the fundamental impulse to exist, to continue, is perhaps the most powerful intrinsic force throughout the living world, operating from the deepest hydrothermal vents to the most exposed, windswept peaks.
Well, we've covered an absolutely astonishing amount of ground today, haven't we? From the blinding pulse of the Big Bang, through the formation of galaxies in our solar system, deep into the Earth's fiery core, across its drifting continents, into the intricate dance of molecules within our cells, and along the unpredictable branching path that eventually led to humanity. It's a story made comprehensible, piece by painstaking piece, through centuries of persistent scientific inquiry, often fueled, I think, by that same fundamental, almost childlike question we started with. How do they know that?
It's a journey of understanding that's far from over, of course. That power of curiosity, that initial spark of wonder when faced with the universe's mysteries, continues to drive scientists today to unpick the deepest secrets of the heavens, the earth, and life itself. Our understanding is always growing, always being refined, challenged, and expanded, and there are surely countless more aha moments waiting out there for the next generation of curious minds.
And this brings us to a final, perhaps slightly sobering, provocative thought for you, our listener, to consider. We, as a species, Homo sapiens, have demonstrated this incredible capacity for unpicking the deepest secrets of the heavens, for understanding the vast cosmic and evolutionary ballet that brought us into being. We can trace our history back billions of years. But at the very same time, as our source starkly reminds us, we've also shown ourselves capable of pounding into extinction for no purpose at all, a creature that never did us any harm and wasn't even remotely capable of understanding what we were doing to it as we did it. Think of the dodo, driven to extinction within decades of human arrival on Mauritius. We have more physical evidence, more fossils, of many ancient sea monsters that lived millions of years ago than we do of a unique bird that lived well into modern historical times, largely due to human actions hunting, habitat destruction, introduced predators. What does this profound duality, this immense capacity for both breathtaking discovery and understanding, and simultaneously for heedless, careless destruction mean for our future on this planet? And what responsibilities come with possessing such vast knowledge and power? That's something for you to mull over long after this deep dive ends.
We certainly hope you found this journey into your own astonishing, improbable existence both enlightening and thought-provoking. It's quite a story.
It really is. Thank you for joining us on the deep dive. We'll see you next time.